talk about advancement operators, I want to get just a little bit into differential equations, because differential equations are really going to be sort of a model for how we think about some of these recurrence equations. Again, you might also find these called difference equations. The requirements and definition for a difference equation are a little bit different, but they're very similar, similar enough that you could just look up difference equations and find information on these recurrence equations or recurrence relations. So let's start by just doing a little bit of review of differential equations. And then we'll look at the advancement operator. So maybe you haven't had like a formal course in differential equations, but I bet if you've had some calculus, you could probably do some fairly basic differential equations. So let's do some really simple differential equation examples, and hopefully this can kind of serve as motivation. So let's find a function f mapping reals to reals such that I want f prime of x to equal 2. Well, if I'm looking for a function whose derivative is equal to 2, I can probably guess it's I just take the antiderivative, right? So if I've had any background in calculus, like formal background in calculus, I should be able to look at this and think, well, I know what that function is going to be. It's going to be the function whose derivative is 2. So solution, let's integrate both sides with respect to x. F prime of x dx equals the integral of 2 dx. And what do we get? Well, we're going to get that f plus c is 2x plus c. Now, remember we have this, this is an equal sign. This is some unspecified constant. But the answer is, f of x equals 2x plus some unspecified constant. So I want you to notice here I've got a c here and a c here, and those just get absorbed into the same c. And that's because any constant here will give me the derivative of 2. So whatever value I pick for c, it'll still, when I take the derivative, solve f prime of x equals 2. So maybe that's not super interesting. So let's do a slightly more interesting example. Because there's this wishy-washy constant there. Let's do something similar. Let's find f mapping r to r, such that, and now I'm going to specify some more things about my function. I want f at 0 to be 7, and I want to know some relationship about the derivative. So I want f prime of x to be 2x. Now, in both of these equations, there's a differential operator, hence the name differential equation. So from here, we can see what a differential equation is. Just, again, a simple example of a differential equation, which is just an equation that has a differential operator in it. So for f prime equals 2x, I can try the same approach. Integrate both sides. Integrating f prime of x dx is integrating 2x dx. And this gives me, I did an equals here. That was low class. Just so happens it does equal, but that should have been a right arrow saying this implies this is the next step. What happens on the left-hand side, again, I get f of x plus c, and on the right-hand side, I'm going to get, the antiderivative of 2x is going to be x squared, again, plus c. So this tells me that I've got f of x is x squared plus some constant, but now let's find this constant by plugging in this initial data. So now I plug in f of 0 is equal to 7, and what does that give me? Well, when I plug in f of 0 is equal to 7, I like to write it like this. I write 7 equals f of 0 equals, then I plug in 0 squared plus c. Oh, look at that. This tells me that 7 equals my constant, which means my final answer is f of x equals x squared plus 7. So in contrast to this previous example, I have an actual explicit term from the constant, which I get from what I'm calling initial data. So if we think about sort of the, like graphically what's going on, this is saying I'm thinking of a function whose slope is 2. And there are infinitely many functions out there whose slope is 2, just lines with slope 2, and then you can vertically shift them, and this c is like that vertical shift. Here I'm looking for any function whose derivative is 2x, so it's going to be a parabola. But not only, so there are infinitely many solutions to this, infinitely many parabolas, but now we're looking for the unique parabola who has f of 0 equals 7, and all the other characteristics, this same other characteristics being, no multiplier in front, no shift or anything like that. So it's got to be a parabola with some vertical shift. This gives us enough information to specify precisely what that vertical shift is. Now I want to talk about the advancement operator. We already kind of touched on how differential equations worked, so let's now focus on the advancement operator. Well, the advancement operator is going to be a, and it's applied to f of n, and it gives us is f of n plus 1. So you'll recall when we defined a derivative, we ended up dealing with, one way to think of it was dealing with these infinitesimally small quantities, and a way of thinking of a derivative was a change in y over a change in x. So this is giving us access to a change in x, or a change in input. We could go further and talk about the similarities between difference equations and derivatives and differential equations, but rather than getting too bogged down into details or definitions, what I want to do is just use this tool and sort of recognize that there are similarities to what we've already seen. So let's just do an example of employing the advancement operator. So let's let f of n equal n squared plus 3. Let's compute, and this is an ampersand, and let's compute a f of n, and let's do a squared f of n. Well, a f of n is just f of n plus 1. So that's going to be n plus 1 quantity squared plus 3, which is n squared plus 2n plus 1 plus 3, or n squared plus 2n plus 4. So when I apply my advancement operator, it just means that I plug in the variable advanced by 1, incremented by 1. When I do a squared of f of n, that's going to be a of f of n plus 1, which is f of n plus 1 plus 1, or f of n plus 2, which is going to be, of course, n plus 2 quantity squared plus 3. And n plus 2 quantity squared will give us, n squared plus 4n plus 4 plus 3 is going to give us plus 7. So that's kind of how this is going to work when we apply the advancement operator to functions. So this is just some sort of basic exercise on how you employ this. Now let's figure out what it can do for us. So now that we've seen the advancement operator and just a little bit about how it works, let's try to use it to do something. So in the next example, we're going to want to use the advancement operator to look at the recurrence equation type problems that we've been doing. So let's find a function f that maps the natural numbers to the reals and satisfies f of 1 equals 2 and a f of n equals 2 times f of n. So if we just unpack the language here, what are we saying? We're saying, well, a f of n is f of n plus 1. We're just saying f of n plus 1 equals 2 f of n. Well, that's, I think, a pretty straightforward recurrence equation. This recurrence equation is just something that doubles over time, and that is f of n equals 2 to the n times something. Well, 2 to the n times what? Let's say times c1. Now this c1, this constant, is going to be kind of like the constants we had when we were doing the differential equations. We had to find this unspecified constant. And the way that we found the unspecified constants with the differential equations was by plugging in what we've called the initial data, or this other sort of restrictive condition. So now we plug that in. So I'm going to plug in 2 equals f of 1 equals, then I'll write this for n equals 1, 2 to the 1 times c1, and this tells me that c1 is going to just equal 1. And I see that my final answer is f of n equals just 2 to the n. It's 2 to the n times 1. And we notice that this doubles every step. So it does satisfy this equation with my advancement operator. And also if I plug in n equals 1, I get that f of 1 equals 2. So this was kind of forcing the advancement operator into the discussion, but it certainly works. Let's use it a little bit more powerfully. Let's make it do a little bit more work for us. So let's try now an example where f of 0 equals 2, and we have f of n plus 1 equals 3f of n. Now, in this case, we're starting at 0. So my function f is going to map the natural numbers union the element 0 to the reals, just as a side note. And this is the type of function that we're going to be looking at moving forward for not, I guess, kind of for technical reasons, but really just for ease of use, for ease of notation, as we'll see moving forward. But don't worry too much about the fact that I'm adding 0 into the natural numbers. If you want to write the whole numbers for this set, or if you consider 0 a natural number, I'm not going to fight with you. This is just how I'm going to write it. So I want to find such a function. And so what is my function? Well, let's start by writing down this advancement operator thing, but I'm going to write it down a little bit differently. So I'm going to write af of n equals 3f of n. And that's just this equation, rewritten with the advancement operator. But now I'm going to use it to organize my thoughts a little bit differently. I'm going to put everything over to one side and get af of n minus 3f of n equals 0. And now that I've got everything over on one side, I can factor out the f of n, and I get a minus 3 times f of n, or a minus 3 operating on f of n, equals 0. Now, what this tells me here is the way I'm interpreting this is I'm operating on the function f of n with this polynomial in the advancement operator. So I could read it here, and maybe it would be a little bit easier for me to use in the previous types of reasoning that I had. But let's just take that, which I already know how to use, and let's interpret it like this. This is kind of an operator theoretical way of writing the information that I already have. So from here, I know, just let's pause for a second. Let's go back to here. From here, I know my function is going to be something like, well, f of n equals 3 to the n times some constant. So how do I find this constant? Well, I plug in this. I plug in 2 equals f of 0 equals, and then I've got, of course, 3 to the 0 times c1. So this tells me that c1 just equals 2. And that's totally fine. So my answer is going to be f of n equals 2 times 3 to the n. And you notice that I didn't need to use this advancement operator stuff, but I just want you to see how I took this recurrence equation thing and I wrote something down using the advancement operator, not as part of the solution, but as just part of the exploration. So let's kind of pause here and do a more involved example, and hopefully this sort of line of reasoning will help us, or maybe not a line of reasoning, but this way of organizing our information will hopefully help us moving forward.